Okay, so we're continuing on with our competing species model. Our differential equations are here. So this is our set of two. And what we've done so far is we've solved for where the equilibrium solutions are. And from that we got four equilibrium solutions altogether: 0, 0, 0, 3/4, 1, 0, and 1/2, 1/2. And so now we're linearizing about each equilibrium. And so we take our system, so we can think of that as our f of xy equals x minus x squared minus xy, and our g of xy, our y prime, was 3/4 y minus y squared minus 1/2 xy. And our Jacobian matrix then is f sub x, f sub y, g sub x, g sub y. So f sub x would be 1 minus 2x minus y, and then our derivative with respect to y is just minus x. Derivative of g with respect to x would be 1 minus 1/2 y, and then with respect to y would be 3/4 minus 2y minus 1/2 x. Good. And now we plug in our points. So at the origin, and then we'll see what happens at 1, 0 maybe next, and then at 0, 3/4, and then at 1/2, 1/2. Okay, so at 0, 0 we get the matrix 1, 0, 0, 3/4. At 1, 0 we get minus 1. You can double check these. I'm just going to write them down to save us a little bit of time. At 0, 3/4 we would have 1/4, 0. Then for the y we get minus 1/2 times 3/4, which would be minus 3/8. And then let's see, 0 for x, 3/4 minus 2 times 3/4. Is that going to leave us with minus 3/4? And then at 1/2, 1/2, we have minus 1/2, minus 1/2, minus 1/4, minus 1/2. All right. So these are the matrices that we use for Poincare. Poincare. So we have the determinant. Oops, let's do trace first. Trace, determinant, and then discriminant if we need to. So the trace here, 7/4, determinant, 3/4. Discriminant would be 7/4 squared minus 4 times the determinant. So we don't really need the value for that, right? We just need to know if it's positive or negative. So that's going to be negative, right? And so that actually gives us a, oops, hang on one sec. That actually gives us a positive 1/16. Okay, and so therefore, in the Poincare diagram, positive, positive puts us in this quadrant, and then if this is positive, that puts us out here, so this is a source. Kind of what we would expect for the origin. At 1, 0, our trace is negative, so that's going to be minus 3/4. Determinant is negative 1/4. And so we could actually stop there. This is a saddle. Right? That's because, where are we? We're down here on the Poincare classification diagram. Okay, at 0, 3/4 we have our trace is that negative 1/2. Determinant is a negative 1/16. And so again we can stop And again, our point is down here, so that puts us as a saddle. And then 1/2 is our last one. And so our trace determinant. Trace is -1. Determinant positive 1/4 minus 1/8 is equal to 1/8. Then the discriminant would be 1 minus 4 times 1/8, which would be 1/2, so that's positive. And so where are we? With a negative trace, we're on this side, right? With a positive determinant, that puts us here. And with a positive discriminant, that puts us here. So this is a sink. Good. So if we look at the XY plane here, we have our origin. We have maybe 1/2 here. And then we have x equals 1, 0 there. And then at 0, 3/4 is our last. So these are our equilibrium solutions, right? And at 0, 0, everything is moving away, right? And then at 1, 0, we have a saddle. And so this is actually the incoming side of things, right? So you can imagine that. And then we have our sink over here, so that means that things are being attracted to points. So I think things are probably going to come in like this, right? That's kind of what it's looking like. And then from here, this is our incoming side of this saddle, and so this would be outgoing here. So it looks like things are moving in this way, maybe in this way. So it looks like everything is moving in towards this 1/2, right? What does that mean? For almost all initial starting positions, what happens to the two populations? X and Y both will, let me say for all initial positions greater than 0, right? If we're on the axes, then we don't have this, but then X and Y will both go to 1/2. So 50-50, a nice beautiful sharing arrangement between the rabbits and the hamsters. Okay, and so one last thing you can do is to verify that using our plotter. And so here you can see the results of that, and so you can see that all of our solutions are heading towards the sink, just like we thought. And notice that normally, physically we wouldn't look at anything in the negative side, but it is possible mathematically, right, to have these negative values. And so we could look at those values if we wanted to, but typically we ignore those. Good. All right. So that is the competing species model. So I think what I'll do next is we'll just set up a slightly different model, and we'll try to answer some questions about it. All right. I'll pause here for a second and write down the equations. Okay, so I just wanted us to think about this system of differential equations that we're looking at here. What's happening to these two populations? We said in the other example that we had two competing species models. Do we have competing species models here? Well, first off, you might notice that in the absence of the other, x prime is just x, right? Which is increasing, kind of an exponential growth model. And in the absence of the other for the y prime is decreasing. And then in the presence of interactions, x decreases, but y increases. So it looks like this is not competing species. This is something called predator, prey. And in fact, can you tell me which is the predator and which is the prey? Just by the signs, the plus and minus signs that you see here. Well, it looks like X is the prey, right? Because in the absence of the predator, X flourishes, you could say. And then Y is the predator. Good. So in the next example, we will just do a quick analysis of the predator-prey equations, just like we did for the competing species. But this is good practice to look at your differential equations and see what's happening. Think about what happens if one of the variables is 0. In one case here we could say, well, what if y is 0? That 0 is everything else except for x prime equals x. And then what if y is 0? Or sorry, what if x is 0? If x is 0, it zeroes out the first equation, and we're just left with y prime equals minus 3/4 y. And so that means that the population for y is decreasing. Good. All right. So we'll talk more in the next video.